Stop scrolling and take a look at these coordinates. 18.38 degrees north, 77.58 degrees east. This isn't a simulation. This is raw telemetry downlinked directly from the Perseverance rover. Focus on the visual data. The image is grainy, high contrast, processed through the Mastcam-Z filter. You see the standard Martian regolith, the endless oxidized rust that we've been staring at since the Viking landers in the 1970s. It's what we expect. It's what the textbooks say Mars is, a frozen, desiccated wasteland. But look closer at the Docks Castle region, right there. Those white anomalies, they stand out like beacons against the red dust. Bleached, pale, anomalous. These aren't just lighter-colored rocks. According to a breakthrough analysis just released by Purdue University in Communications, Earth, and Environment, these specific geological formations represent a mathematical impossibility under the current cold Mars model. For 40 years, the official line from NASA and the global scientific consensus has been safe, conservative, and boring. They told us Mars was cold. They told us any water that existed was frozen or transient to flash flood here, a sublimating ice sheet there. They built an entire history of a planet based on the idea that it was always too hostile for complex, sustained biomes. That history is wrong. The data just broke the model. Dr. Adrian Brose, Purdue University. He didn't just look at the pictures. He looked at the spectroscopy. He looked at the chemical absorption lines. When the Perseverance rover fired its SuperCam laser at these white targets, specifically a target named Mist Park, the vaporized rock plasma gave off a spectral signature that shouldn't exist on a dead planet. It wasn't basalt, it wasn't simple sandstone, it was heavy in aluminum and depleted in almost everything else. This is a signature for a mineral called kaolinite, but not just any kaolinite. Let's look at the chemistry. On Earth, you can find this kind of mineral in places like the Amazon basin or the deep tropics of Southeast Asia. You find it where the rain never stops. To get rock this bleached, this stripped of its original iron and magnesium, you need water, but not standing water. Standing water doesn't do this. A lake doesn't do this. You need rain. Torrential, relentless, hot rain. We are talking about millions of years of heavy flushing. A hydrological cycle so aggressive that it literally washes the iron out of the rock structure, leaving behind this white, ghostly skeleton of clay. The implications of this specific chemical ratio are terrifying for the established timeline. It means Mars wasn't just wet. It means Mars was tropical. It means the atmosphere was thick, hot, and heavy with moisture. It implies a greenhouse effect massive enough to support a global rainforest system. We aren't looking at a few rocks. We are looking at the fossilized remains of a climate that looked more like Jurassic Earth than the Mars we know today. The official narrative tries to contain this. They say, well, maybe it was localized. They say perhaps it was geothermal. But the SuperCam data is stubborn. The degree of weathering, the sheer percentage of ion depletion requires a volume of water that is staggering. And here is where the story pivots from interesting to disturbing. These white rocks, the ones telling us about this ancient rainforest, they don't belong in the Jezero crater. The rover's navigation logs confirm it. The local bedrock is sedimentary and volcanic. It matches the cold Mars profile. But these white stones are afloat. They are loose. They are scattered on top of the surface, disconnected from the geology beneath them. They came from somewhere else. The Purdue analysis admits this. These rocks were transported, but from where and how? If they were washed in by a river, where is the massive delta required to move stones of this density? If they were ejected by an impact, where is the crater deep enough to expose a tropical layer that should be buried miles underground? The data presents a paradox. We have physical proof of a hot, wet, living Mars sitting right on the surface, staring into the camera lens. Yet the surrounding terrain shows a frozen desert. It's as if a piece of a different planet was dropped onto the surface of this one. The timestamps on the data packets are clear. The analysis is peer-reviewed. The chemical composition is undeniable, but the context is missing. NASA is calling this a benchmark for understanding Martian climate. That is a soft word, a safe word. The reality is in the numbers. The amount of chemical weathering found in the Mist Park samples suggests a climate stability that lasted for epochs. You don't get this level of leaching in 1,000 years. You don't get it in 10,000. You need stable, high-pressure atmospheric conditions for millions of years. And then, suddenly, it stopped. The rain turned off. The atmosphere vanished. The rainforests bleached into white clay and were scattered across a freezing desert. What kills a planet that is this alive? We aren't talking about a slow decline. The existence of these rocks on the surface, unburied, suggests a geological violence that we haven't accounted for. Look at the spectral graph again. See that spike in the aluminum channel? That is the tombstone of a world that shouldn't have died. And the fact that we are just finding this now, years into the mission, buried in a sublayer of a PDF report, suggests that the people running the mission didn't expect this either. They sent a rover to find signs of ancient microbes. Instead, they found the wreckage of a jungle. Pull up the spectral graph from the SuperCam instrument. This is the raw data file labeled Mist Park. It is not a photograph. It is a chemical interrogation. Focus on the absorption band at 1900 nanometers. Then look at the overtone at 1400. To the untrained eye, these are just dips in a line graph. But to a geochemist, these dips are a signature. They represent the vibration of water molecules trapped inside a crystal structure. This is the fingerprint of heavy, aggressive hydration. The Purdue University analysis was exhaustive. Led by Dr. Adrian Brose, the team didn't just guess. They overlaid this Martian signature against geological databases from Earth. They compared it to the weathering profiles of the pan-tropical belt, specifically the deep clays of Malaysia and the ancient paleosols of South Africa. The spectral match was nearly absolute. On Earth, rocks don't turn into this specific type of kaolinite by accident. You cannot get this purity from a standing lake. You cannot get it from groundwater seeping up through the cracks. You need a process called hydrolysis. You need rain. You need water falling from the sky with enough frequency and enough heat to strip the rock of its identity. The data shows that these rocks have been depleted of iron. They have been depleted of magnesium. Those elements are heavy. They don't just leave. They have to be washed out. This implies a water-to-rock ratio that is staggering. We are talking about millions of gallons of fresh water flushing through the soil column for hundreds of thousands of years. The official NASA press release calls this aqueous alteration. That is technical sanitization. Aqueous alteration could mean a wet sponge. What the numbers show is a monsoon, but the data packet contains a contradiction that most mainstream reporting ignored. Zoom out to the orbital map of Jezero crater. The rover is currently traversing the crater floor. The geology here is well understood. It is a mix of volcanic floor units and sedimentary delta deposits. But these white rocks, they don't fit the unit. In geology, we call these float. Float is the term for a rock that has been displaced from its original source. It is an orphan. It is sitting on terrain where it does not belong. The navigation logs confirm that these white stones are scattered loosely across the surface. They aren't embedded in the bedrock. They aren't part of the stratigraphy. They are debris. And this creates the transport problem. How do you move a rock formed in a high-altitude rainforest down into the bottom of a crater without destroying it? The official explanation offered in the Communications Earth and Environment paper suggests impact gardening or meteorite ejecta. The theory is that a meteor hit the crater rim, blasted the rainforest soil into the air, and it landed here. But look at the physics. Kaolinite is soft. It is a clay mineral. It is fragile. A meteorite impact generates heat in excess of 2,000 degrees Celsius. It generates shock waves that vaporize water and fuse silica into glass. If these rocks were blasted out of a crater by a hypervelocity impact, they should be shocked. They should be glazed. The delicate hydration signals, the very signals that prove they are from a rainforest, should have been baked out of them. They weren't. The SuperCam data shows the clay structure is intact. The hydration is preserved. This means they weren't exploded. They were moved. Dr. Brian E. Horgan, a co-author of the study, is on record stating, "We're not totally sure where they came from." That admission is critical. When the lead scientists on a $2.7 billion mission admit they don't know the origin of the most significant geological find of the decade, it means the standard models aren't working. It suggests a mechanism of transport that we aren't seeing. The silence regarding the violent nature of this displacement is where the narrative cracks. If the rainforests were on the crater rim and the rocks are now on the floor, and they weren't thrown by a meteor, then how did they get here? Massive flooding? Glacial transport? Both of those require a climate even more extreme than the one that formed the clay. We are looking at a geological sequence that is broken. We have the official Mars the cold dry desert we see today. And sitting right on top of it, we have the impossible Mars chunks of a tropical system that have been ripped from their source and dropped, pristine, onto the rust. The transition isn't gradual. The rock record doesn't show a slow cooling. It shows a snap. One distinct geological era sits directly on top of another, with no transition layer in between. This brings us to the scale of the threat. If Mars was capable of sustaining a climate this rich, this wet, and this stable, it implies a thick, protective atmosphere. It implies a planetary shield. And yet, the debris field suggests that this system didn't just fade away, it was dismantled. The presence of these rocks is evidence of a chaotic event, a global disruption that didn't just dry out the planet but physically scattered its geological history across the surface. The data doesn't lie. The chemistry is tropical. The location is wrong. The transport mechanism is unknown. NASA is currently driving Perseverance toward the crater rim to try and find the parent outcrop, the source of these white stones. They are hoping to find the rest of the rainforest, but the data suggests they might only find more debris. The implication of this discovery is not just geological, it is existential. When you look at a white rock that used to be a rainforest soil, you are looking at a tombstone. We are staring at the physical wreckage of a planetary system that was, by all metrics, alive. It had the heat, it had the pressure, it had the hydrological cycle to wash mountains into clay. And then, it stopped. This is the uncomfortable truth that NASA's data forces us to confront. We like to believe that planets are stable. We tell ourselves that Earth is a fortress, protected by a magnetic shield and a thick atmosphere that will last forever. We look at Mars and say, it was always small. It was always doomed. But the kaolinite in the G0 crater destroys that comfort. To get that specific chemical weathering, Mars needed a thick, insulating atmosphere. It needed a shield. It was, for a time, a twin of Earth. And yet, it was stripped. The MAVEN orbiter has been tracking the escape of the Martian atmosphere for years. It confirms that the solar wind is stripping ions from the planet every second. But the presence of these tropical rocks suggests the process wasn't just a slow leak. If the transition from rainforest Mars to dead Mars was gradual, we would see a gradient in the rocks. We would see the clay slowly mixing with the sand. We would see the chemistry fade. We don't. We see a hard cut. We see pristine tropical clay sitting on top of a frozen wasteland. This presents us with a paradox, a choice between two terrifying options. Option 1, the great filter is real. This theory suggests that planetary atmospheres are temporary. It suggests that the stability we enjoy on Earth is a statistical anomaly, a fluke. If Mars could hold a rainforest and then lose it all to the vacuum, it means the Goldilocks zone isn't safe. It means a slight shift in the magnetic core, a minor wobble in the axis, or a fluctuation in the sun is enough to turn a paradise into a rust bucket. It implies that we are walking on the edge of a knife, and we don't even know it. The silence of the universe isn't because there is no life. It's because life doesn't last. It blooms, it builds a rainforest, and then the planet kills it. Option 2, the cataclysm. This is the option the geologists are whispering about. Remember the transport problem. Remember the float. These rocks were ripped from their source. They were scattered. They are debris. This supports the theory that Mars didn't just die. It was murdered. A catastrophic event in impact, a crustal displacement, or something we haven't identified yet didn't just change the weather. It shattered the surface. It ejected the rainforests from their foundations and threw them across the equator. It turned the biosphere inside out. If this is true, then Mars is a crime scene, and the perpetrator is still out there. We are scanning the sky for asteroids. We are monitoring the climate. But we are looking at the problem through the lens of human history, which is short. The rocks in Jezero crater are looking at us with the weight of geological time. They are screaming that safety is an illusion. The Perseverance rover is continuing its climb. It is heading toward the rim. NASA hopes to find the parent unit, the massive deposit of ancient soil that these rocks came from. But what if they get there and find nothing? What if the white rocks are all that is left? The universe is efficient at erasing mistakes. The question you have to ask yourself is simple. Is Earth the exception? Or are we just next in line? Look at the evidence. Look at the chemistry. Look at the silence. I want you to make a choice based on the data. Do you believe Mars died because of a natural cycle? Or do you believe the scattered debris proves a violent event killed it? Go to the comments. Type C. Weichel if you think planets just naturally die. Type IMSACT if you think something destroyed it. I will be pinning the best theories.